Okay, welcome back. This time we're finding volumes using the shell method, and we'll start with an x-axis rotation. This method is used, I mean, you could always use the disk method, but sometimes it will become hard because you'll have multiple regions you'll have to do. So it may be easier to just do the shell instead. So we offered this method as kind of an alternative. So you should know both methods, because you can find problems where there's just no way you can do it with a disk or washer. You're kind of forced into doing it with a shell. So anyways, let me start with kind of deriving the formula. I'll go with this picture they have in the book, figure 7.28. So with shells, the rectangles are going to be parallel to the axis of rotation. That's a little bit different than what we saw with our disk and washer method. So here's one of our rectangles, that red thing, for the shell method, and we're going to rotate it about the x-axis and generate this new object such that the Riemann man is going to run up the flagpole in this orientation and collect that basically the volume of these new objects, which will be shells. So maybe integrating from C to D. This picture, we may need an extra value here. Let's put A right here. All right, so what is the object that the Riemann man is collecting this time? What the volume? So it's going to be this kind of shape. It's basically a cylinder again with the hole removed, right? Or with the middle removed. Looks like that, I guess. And let's put the axes in here for reference. Three-dimensional. Okay, so the red rectangle, where is it? It would be positioned right here in this object. And we're rotating that red object about the x-axis, and it's creating this object. We want to find the volume of that object, and that's what the Riemann man is going to collect when he goes up the flagpole. Okay, so rather than do what they do in the book, I'm going to do what they do in a different book and cut that shell and then lay it flat. The resulting object is a rectangular solid, so it's just length times width times height. That should be a little bit easier to sort of generate than what they do in the book. The red rectangle in this orientation now is right here on the edge. Okay. So this dimension here, this first dimension, you can just say is g of y sub I, basically the height of that red rectangle. And I know there's a little space in there. If you want to, you can subtract away g of y sub I minus a, I guess, would give you this distance. Okay. Then the width of this red rectangle is going to be change in y. So that dimension is it's this dimension here. So this is change in y. And then the only dimension you're left with figuring out is this length here. That turns out to be the circumference of that object. So it's going to be 2 pi times the radius. And the radius is the distance from the x-axis to that particular rectangle. And you can see to the side that's just going to be y sub I in this case. In general, we'll say it's a formula, rho of y or p of y. It looks like rho looks like a p. But in this case, it just turns out to be y sub I. Okay. Okay, so the volume increment this time, the delta V that our Riemann man is going to be collecting in his little packet here is just length times width times height. So in this case, 2 pi y sub I times g of y sub I minus a times delta y. Okay, and let's make that general. So in general, our delta v sub I is going to be 2 pi times some radius function, which we're going to call rho of y, and then times some height function, h of y sub I, delta y. So these two functions are kind of what you're going after when you set up your problems. So with the disk in the shell method, you were looking for a radii, right? A radius function. For the disk method, for the shell method, for the washer method, then you were looking for a big radius and a little radius function. Now you're going to be looking for a radius function and a height function. Okay, and then for your integral, in this orientation, we have basically just the sum of these increments. So it'll be the integral. You can factor out the 2 pi from c to the d in this case of rho of y times h of y delta dy. Okay. Okay. So that's the idea. That's the formula for us. There's vertical and horizontal axis of rotation. So this was around the x-axis, but you could also do rotations about the y-axis. So if you have some figure like this, rotating around in that direction, your rectangles will look like this. So the bases will be on the x-axis, and you'll have some x of I. So this would be some f of x function, and so your functions that you're after, the rho of x, the radius function would just be, in this case, the x, and the height function would just be the f of x, and then our integral would be 2 pi integral from a to b, assuming this is a and this is b, rho of x, h of x dx. Okay, so again, when we did disk and washer method, note all the rectangles are perpendicular to the axis of rotation. Right? If I'm going around the x-axis, there's my rectangle, it's perpendicular. Going around this shifted axis, the rectangle's perpendicular to it. Here the rectangle's perpendicular, we were rotating about the y-axis. Right? So then when we get the shell method, the rectangles are parallel to the axis of rotation. Okay, so let's take a look at example 1 here in the book. They want you to find the volume of the solid formed by revolving this function, y equals x minus x cubed, and the x-axis about the y-axis. And we're going from 0, let's go to the axis. So let's get a picture going here. Let's see what we're dealing with. So this function, you can set it equal to 0. Factor out the x, you get 1 minus x squared. So it's going to have this behavior, and its intercepts would be 0 and then plus minus 1. Okay, so let's get a little picture going. It's a terrible picture, but there we go. Minus 1 plus 1. It's going like this, and then it's probably going to go like this, and then down like that. Okay. We're going from 0 to 1, so this is a region we want to rotate. We want to do it about the x-axis. Remember, the shell rectangles are parallel to the axis of rotation, so it should look like this. The base is on the x-axis, so your radius function and your height function will be in terms of x. The radius function is the distance to the rectangle, and in this case, it's just plain old x. The h of x is the height of the rectangle, so that would be x minus x cubed. Okay. In general, if you're doing a rotation about the x-axis or the y-axis, so just a note here, if rotating about the x-axis, your rho of y will automatically be y. If you're rotating about the y-axis, your radius function will automatically be x. Okay, so just to the side. Okay, once we've established all that business, we plunk it into our formula. So 2 pi integral x times x minus x cubed. We're integrating from 0 to 1 dx. Distribute. So we have x squared minus x to the 4th dx. Integrate. So we get 2 pi times x cubed all over 3 minus x to the 5th all over 5. Evaluate the antiderivatives at the limits of the integral. So putting in 1 first, you get 1/3 minus 1/5. Of course, put in 0, you get 0. Find a common denominator here. 5/15, 3/15. That'll give you 4/15 pi for the volume of that thingamajig. Okay. Note this thingamajig. It's kind of like the bottom of a bagel, I guess. If you were to rotate it, it would look like a bagel. If you tried to do the washer method, it wouldn't be a lot of fun. In particular, you would not have a nice function to deal with. You would have to cut it into 2 regions, and I'm not even sure how I would go about doing that. So the point being, it's often very hard to determine how to do it in one other method. So if it looks like a shell method, it may be impossible to do it using a disk method, and vice versa. Let's look at example 2, and I think they're really trying to send that message home. In particular, trying to find the inverse of this function. So if you were going to do the other method, I think that would be pretty hard. But anyways, let's look at what this thing looks like. E to the negative y squared, I know that from statistics and probability, that's like a normal curve. So if it was in e to the negative x squared, it would look like this. It's e to the negative y squared, so it's probably going to look like this. Okay. They want you to go from y equals 0 to y equals 1, so it's this region right here. So let me inflate that a bit and kind of draw that. Okay, so it's like a sideways bell-shaped curve. We want to go about the x-axis. Remember your rectangle's shell parallel. Okay, so there's one rectangle. Its base is on the y-axis, so we're with respect to y. And the radius automatically, the radius function y of rho of y will just be y. And then the height function will be from the e to the negative y squared. Okay. And so I think we could just plop that into our integral and go to town. Let's see if we're going from 0 to 1. It says that in the problem. Go from 0 to 1. What else do we? Oh yeah, so the integral 2 pi integral 0 to 1 of y e to the negative y squared dy. I'm going to have to do a u sub. So u is negative y squared, du is negative 2y dy, and then dy is negative du all over 2y. So box all that material off. And you get 2 pi integral y e to the u times negative du all over 2y. And then that will equal, you can factor out the negative 1/2, the y's cancel. So you get negative pi integral of e to the u. E to the u is just, the integral of e to the u is just e to the u, so you can just dispense with those pleasantries. You have the back sub, so e to the negative y squared from 0 to 1. And then we have plugging in the limits. So e to the negative 1 minus e to the 0. So you're going to get negative pi times 1 over e minus 1. Yeah, so that would be your answer. Yeah, so there's that. Yeah, and then they make this note right here. If you tried to use the disk method, you would have to put the shell. So first you would have 2 regions, right? You would have this first region where your rectangles would be like this, and they have the second region where your rectangles are like this. And that second region, you would need to find the inverse of this formula right here and for your integral, right? So your radius function r of x for that second region would be, and you can see it here to the right, the square root of negative ln of x. We don't know how to integrate that thing just yet. I mean, when you put it into your integral, right, it's going to be pi from whatever point that is to to 1. But in here you'll have negative ln of x, right? Because it's pi r squared dx, and we don't know how to integrate the natural log yet. We will learn how to do that, but right now we don't even know how to do it. So you wouldn't be able to do the disk method is the point. Okay? You got to learn this method. Is what they're. So now they're actually going to compare the disk and the shell methods in a couple of problems. Let's take a look at example 3, I guess. Find the volume of the solid formed by revolving the region bounded by the graphs of y equals x squared plus 1, y equals 0, x equals 0, and x equals 1 about the y-axis. Okay, so x squared plus 1 is just a shifted parabola. Just go up 1 like this. Y equals 0 is the x-axis, x equals 0 is the y-axis, and then x equals 1, is out here somewhere. So it's this region we're after, and we want to do a y-axis rotate. Okay. If you do the shell method, your rectangle is going to be like this. Shells are parallel, and that should be pretty simple. Your radius function is just the distance to the particular shell. So in this case, it's just x. The height function, pretty simple as well. It's x squared plus 1. So your integral is going to be from 0 to 1, 2 pi x times x squared plus 1 dx. Pretty simple. Okay. Let's look at the other variation then. So if we want to do disk method, it's going to be kind of a nightmare, right? And so the disk, the little rectangles are perpendicular, so you're going to have 2 regions first off. This first region is pretty simple. So region 1, the radius function, and the base is on the y-axis, so it's in terms of y. The radius function is just 1. Region 2, when you rotate that thing, it has a hole in it. So basically you have to do a washer on it. There'll be 2, your big R of y is again going to be 1. Your little r of y is going to be from the inverse of y equals x squared plus 1. So let's get that. It's x squared equals y minus 1, and then x equals plus minus square root of y minus 1. We want the positive branch. So this curve here would be your square root of y plus 1. So this little r of y would be square root of y plus 1. And so you'd have an integral from 0 to 1 of pi times 1 dy plus the integral from 1 to whatever this point is where 1 intersects with that. I believe it's 2. Well, let's see. So it's yeah, just put in 1 for x. So that'll be 2. Well, it's on. I'm going on the y-axis, so it's not, is it? So it's you're taking y equals no, it is 2. This point right here. Whoops! I just annihilated my entire graph. This point right here, I'm after the y-coordinate for it. The x-coordinate is 1, and then if you plug 1 into the parabola, you get 1 squared plus 1, which is 2. So the other limit on the integral will be 2 pi, and then you have 1 squared minus the square root of y plus 1 squared dy. I mean, you could do that. It's not that bad of an integral, but at the end of the day, I'd rather do 1 integral than 2 integrals any day. So the shell method, in this case, I would say is superior. Okay, so they're showing here is the the sort of disc and then washer. And here they show you the calculations for the shell method. And I think it's kind of clear that the shell method is a little shorter. Okay. Here they are talking about rotating example 3 about a different line. So we can take a look at that real quick and see how that works. So what do we have? Example 3. Let's make this the video quiz. So rotating about this other line. Let me mark in my notes. So this is the third question on video quiz set number 3. 7.3. It's basically example 3 from the book, but you're rotating about a different line. About, I think they said x equals 1. Okay, so the same set of curves, y equals x squared plus 1, the same region basically, right? So y is 0, x is 0, x is 1. X equals 1 rotation. So let's get the picture. Here is our graph. That's the region we're rotating, but this time we're going about this line x equals 1. Okay. Shell method all the way, and here is a particular rectangle. The issue when you're doing a non-axis rotation is it changes your radius function. Okay, so here the radius function is in terms of x, and then we need a height function as well. The radius function now is the distance from, it's always the distance from the axis rotation to the rectangle, okay? So it's not just going to be x, right? It's not. It's x would be this distance from here to here. So it's a difference, right? It's the difference between 0 to this line, which is 1, and the distance to the rectangle itself, which is this distance. Okay, let me draw that a little better. Okay, so the blue distance is what we're after. And what I'm saying, let me put this difference in red. Well, maybe yellow. What I'm saying is that distance there is a difference between this distance and the distance to the rectangle. Okay, so the big rectangle, that distance is just 1. The distance then of the little rectangle is the distance to the rectangle, which is just x. Okay, and then your h of x is just the function as usual. So your integral will be 2 pi integral from 0 to 1 of p of x minus h of x dx. And then we can integrate that fairly easily. So we're foiling first, outer, inner, last, dx. 2 pi integrate x cubed over 3 plus x minus x to the 4th over 4 minus x squared over 2 from 0 to 1, and then that will be 2 pi times 1/3 plus 1 minus 1/4 minus 1/2. Want a common denominator amongst all this junk. So I guess we're making that 12. So this would be 4 over 12, 12 over 12, 3 over 12, and then 6 over 12. So 16 minus 9, which is 17/12. And then times 2 is going to give me 17 pi over 6, I believe, unless I made some drastic error in my calculations. Let me try that again. So 1/3 plus 1 minus 1/4 minus 1/2. Make sure everything looks correct, because I don't think they give you the answer. No, they don't. Kind of like that. So it's 1 minus x. So So x squared, first outer 1, inner minus x cubed, last minus x cubed over 3 plus x minus x to the 4th over 4 minus x squared over 2. So it's 1/3 plus 1 minus 1/4 minus 1/2 on a common denominator. So 4/12 plus 12/12 minus 3/12 minus 6/12 16/12 minus 9/12, which is 7/12. Ooh, I did mess it up, didn't I? Can't trust myself to do anything anymore. So I think that's, yeah, that will be your video quiz. Hopefully that's right. If not, make a correction to it. Don't blindly just copy what I do, even though I'm encouraging that at this point. But anyways, let's look at example 4. We're looking for the volume of a pontoon. They give you a parabola, 1 minus x squared over 16 from -4 to 4. And let's get a graph of this thing. So upside down parabola, shifted up 1. It'll intersect at -4 and 4. Okay. So it's this region, and they're rotating it about the x-axis. Again, shells are parallel. So this is kind of a bummer, because it looks like we're going to have to maybe do some trickery to get the answer. One way to do it is to cut it in half and just integrate from, so my Riemann man is going in this direction. So you see there's kind of an issue there. He's going from 0 to 1. It'd probably be easier to do it using the disk method, because the way it is now, you kind of need to solve for y, or rather solve for x, right? And it'll give you 2 branches, that blue one there, and then this yellow one. You could kind of make it a little easier just by considering this region and then multiplying it by 2. So you would have for your, you would have to solve that. So y equals 1 minus x squared over 16. So x squared over 16 equals 1 minus y. And that would give you x squared equals 16 times 1 minus y. And then x would equal 4 plus or minus 4 times 1 minus y. But you could just use the plus version, square root of 1 minus y. The blue version, and then go and say my radius function is y, my height function will be 4 times the square root of 1 minus y, and then go 2 pi integral from 0 to 1, and then you have to multiply it by 2, because I've assumed I'm only getting this one region rotated. But if you multiply that volume by 2, you'll get the whole pontoon. So 2 times 2 pi times y times 4 times the square root of 1 minus y dy. But what I'm saying is it's probably easier to just do the disk method. So for the disk method, there's your blue rectangle, and your Riemann man would be going like this. So this is the shell. Let me put that in black. This is sort of your shell integral right here. So for your disk integral, let's take a look at that. Your radius function is what it is. It's just given as 1 minus x squared over 16. So you'll have the integral pi from -4 to 4. If you want to cut it in half and multiply it by 2, that's fine as well. Then 1 minus x squared over 16 squared dx. And that's what they do. They do the disk method. They don't even mess around with the other method. Yeah, the other method is nasty, because this shell integral right here, you'd have to do a u sub on the 1 minus y, and then you would have to rewrite the y in front of it as 1 minus u, and it would just be kind of annoying. Example 5, they're saying you have to do a shell method, so they're kind of like forcing you, you know, you have to do this method because they're giving you one of the function's a cubic, and you're not going to have any choice. Let's try that. So the function is y equals x cubed plus x plus 1. We got some boundaries here. Y equals 1, x equals 1. We want to rotate about x equals 2. They give you a picture, so we have to get too carried away with the deal. But at 0, it's going to be 1, and it has a cubic kind of behavior, so it's going to go up like that. We have y equals 1, which is this line here, and then x equals 1. So at 1, y, the cubic will be 3. So if you plug in 1 for x, you just get 3. This point here is at 1, 3, folks. There's x equals 1. So here's the region that we're after, and we want to rotate about the line y equals 2, which is this line here. Okay, so again, shell is parallel. There's our little rectangle for the shell method. Its base is on the x-axis, basically, so you're doing this with respect to x. So you'll need a p of x, which will be not x because of the shifted axis of rotation, and then you need a height function, which will be a little different as well. So the p of x, first of all, is going to be this distance from the axis of rotation. Okay. To get that distance, you think of it in terms of differences, right? It's really this distance minus the distance to the particular rectangle. Okay, so the big distance is 2, and then the littler distance there is just x, the distance to the rectangle. Okay, the height function then again is a difference. It's the distance to the top of that little red rectangle in here, minus the distance to that line below it. Okay, that will give you the height of those rectangles. So the distance to the top of that red rectangle is given by the cubic, so that would be x cubed plus x plus 1. And then you're subtracting away the distance to the bottom. So that's just 1. Okay, so here you have x cubed plus x, and let me rewrite this in black. So our integral will be 2 pi integral going from 0 to 1, and our two parts, the 2 minus x times x cubed plus x dx. And then you just FOIL that and integrate it, and you should be good to go. Okay. That's really all the book has as far as examples. Let's maybe dive in a bit to the homework and see what we're dealing with. Okay, so number 5 looks kind of nasty. Use the shell method to write and evaluate the integral for this region revolving about the x-axis, y equals 1 over x. And we're here going from 6 to 7 on the x-axis. So 1 over 6, we'll say this is 1/6, and then 1/7 below it. So we end up with this kind of picture. And the region we're rotating is this region. And we're doing it about the x-axis. Okay, so shells are parallel. So here's a typical shell. We have an issue, right? We're going to have to put it in the 2 regions. So there's going to be another region up here. And this region, the height of the shell is variable. The height of the rectangle, rather, is variable. Okay, and the first region, it's not. Anyways, the bases of those rectangles are on the y-axis, so everything's going to be in terms of y. And let's work with our regions, right? So region 1 is this part. And So our radius function r of y is just going to be y. It's just the distance from the rectangle to the x-axis. The height function is 1. It's always the height of this rectangle is always going to be 1 in that region, no matter where you are, right? So if the rectangle's down here, it's height 1. 7 minus 6 is 1. If it's up here, the height is 1. So it's just always 1. It's constant. Okay. Region 2, the radius function, again, is just the distance to the rectangle, which is y. Then the height function, a little bit different this time. It's basically this height to the curve minus the height to the bottom of the rectangle. Okay, so the height to the curve, I'm going to have to rewrite this. I'm going to have to solve for x, find the inverse of the function, basically. So x would equal 1 over y. So I'll have, for the longer rectangle, 1 over y, this part of it, this distance, 1 over y. And then this distance is just 6, so minus 6. Okay, so I have an integral from 0 to whatever this point is, and this point is at 7 comma 1/7. This point here is at 6 comma 1/6. Okay, so I'm going from 0 to 1/7 at first. That'll be fun to evaluate. 2 pi y dy plus the integral from 1/7 to 1/6 of y times 1 over y minus 6 dy. Okay. And they're not asking for a decimal approximation, so you're going to have to get an exact answer. Lost my 2 pi there. So the first integral, 2 pi times y squared over 2. So that's just pi y squared from 0 to 1/7. Second integral, we have y minus 6y when you distribute. That first integral then, the first result here will just be pi over 16. That's 2 pi times y squared over 2 minus 6y squared over 2 is 3y squared. Evaluated, that'll be fun. So pi over 16 plus 2 pi times, let's distribute the 2 to get rid of the fraction, right, shall we? So I have y squared minus 6y squared. At least we can get rid of that issue. From 1/7 to 1/6. So that'd be pi over 16 plus pi times 136 minus, those are both y squared, really? No, the first one's a 1. So I mean 1, then this thing will just be y. Sorry. And then this thing is, that thing would be 2y then. Yeah, I wouldn't need to distribute the 2 now, but oh well, life goes on. Okay, so the first guy is 2 times 1/6, which is 1/3. The second guy will be negative 6 times 1 over 36, which will be negative 1/6. And minus 2 times 1/7 is 2/7, minus 6 over 49. That's not so bad. So pi over 16 plus pi times, this will be 2/6, if you wish. So that would be 2/6 minus 1/6 is 1/6, minus, you can get 49, this is 14, excuse me. 14 minus 6 will be 8 49ths, so minus 8 all over 49. And then probably need some common denominators, so let's go a Wolfram here. So 1 over 16 plus 1 over 6 minus 8 over 9 is a nice round number, of course. 155 all over 2352 pi. So let's take a look. And of course it's wrong. So let's see what I did wrong. Oh, I see. When I wrote my 7, it looks like a 4. This right here should be 1/7. So this would be pi over 49, 49, 49, 49 in there. So let's see if that makes a difference. Over 49. Oh, that is a nicer number. Isn't that nice of them? So pi over 42. Let's try again. Yay! All right. This one always gives people trouble for some weird reason because the line is going underneath the graph there. Let's take a look-see at what we got going on. So 1, 2, 3, 4, 5, 6, 7, and then it's going down 1 over 1. It's down 1, 2, 3. 1, 2, 3. Down 1 over 1. Down 1 over 1. Down 1 over 1. Here's our picture. 7, 8, 9, 10. You want to rotate this junk, so y equals 7 minus x about the x-axis. Surreal. Our Riemann man is running like this. The rectangles look like this, so it's with regards to y. And so our radius function is just going to be negative y, right? So negative y, because these positions, the Riemann man is first hitting, they're all negative. It's a negative distance, right, from here to the rectangle. And you need it to be positive for the radius function. So when you multiply it out, you get a positive number. Okay, the h of y, the height function, is the distance to this line here minus the distance to the curve. Okay, so the distance to the line is 10 minus the distance to the curve. So I need to solve that for y, or for x. So I have x equals 7 minus y. So 10 minus 7 minus y. And that should give you the radius. And you could spot check it, like put -2 in there. And I mean, you know what some of these are going to be, right? So this value right here at -1, that rectangle, its height, when y is -1, should be 2, right? The h of y should equal 2 in that case. So what is h of -1? Well, let's clean this up a little first. 10 minus 7 is 3, and then plus y, right? So if you plug -1 into that expression, you get 3 plus -1 is 2. So at least in that case, it seems to work, right? Okay, so let's use those things. I got 2 pi. My Riemann man is going from this point here, which if you think about it, that's going to be at 10, comma 7 minus 10 is -3. So the Riemann man is going from -3 to 0. And we are integrating -y times 3 plus y dy. Okay, so that would be 2 pi integral -3y minus y squared dy, and then you should be home free at that point. So it's 2 pi times -3y squared over 2 minus y cubed over 3. From -3 to 0, so that would be 2 pi times -3 squared is 9, so -27 halves minus plus then 27 thirds. Common denominator. Ooh, I don't like that. It's going to be negative then. Well, odds are you can just make it positive and it'll work for you. Did I put in -3? Yeah. 7. Oh, I see what I reversed the, so I got to put 0 in first. That'll make a difference. So plugging in 0 first, like I'm supposed to, I would just get 0 and then minus whatever, right? So now I put in the -3 and I get -3 times 9, so that's -27 halves. Then minus, that become plus 27 thirds. So that'll be 2 pi times 27 halves minus 9, which of course is 2 pi. I don't know why I put that over 1, but there it is, 27 halves minus 18 halves, which will be 2 pi times 9 halves. So that would be 9 pi, I believe. My arithmetic is just going in the trash lately, but there we are, 9 pi. Okay. Hopefully you could do the rest. Maybe we should do the torus problem. Everybody seems to have trouble with the torus, and then I'll let you go. So torus is formed by revolving this x squared plus y squared equals 1 about the line x equals 2. Okay, so we have a circle with radius 1, and we're going about this line y x equals 2. Okay, so again, shells are parallel. We need this guy right here. The Riemann man is going in this direction. So everything's in terms of x. And we need a radius function and a height function. So the radius function is you gotta be a little careful. It's the distance to the axis of rotation. So it's this distance here in particular. That will be 2 minus x. So radius function is 2 minus whatever your x is. Height function, I could solve this thing for y. I get y squared equals 1 minus x squared, and then y equals plus or minus square root of 1 minus x squared. The plus version is the upper hemisphere of the circle, right here. So I can use that formula to get half the height, because that will just tell me the height of this rectangle. Okay, so it'll be square root of 1 minus x squared. So to get the full rectangle, I have to multiply it by 2. So I get 2 times the square root of 1 minus x squared. Okay. Okay, so I'll have 2 pi integral from this point to this point on the picture. So this is -1 to 1. And then I have p of x times h of x dx. And this is a nasty little integral, but turns out you can use a lot of geometry to figure it out. Just first distribute this whole thing into here and create 2 new integrals. So you get 4 square root of 1 minus x squared dx minus 2 pi times the integral of 2x square root of 1 minus x squared dx. The first integral, you can factor out 4. You get 8 pi times the integral of the square root of 1 minus x squared dx. The second integral, you can factor out the 2, so you get 4 pi integral x square root of 1 minus x squared dx. The first integral, they give you a hint. They tell you that that integral represents the area underneath the semicircle. So in particular, this integral represents the area underneath the semicircle that has radius equal to 1. Okay? So that area is just 1/2 the area of a circle with radius 1. So it's 1/2 pi r squared, so 1/2 pi. R is 1, so it's just 1/2 pi. That thing in blue equals 1/2 pi. Okay, so you get, for your first integral, 4 pi squared. 1/2 times 8 is 4, and then pi times pi is pi squared. The second integral, believe it or not, is going to be 0. Okay? And it's because this thing in here is an odd function. And you may remember that from Calc 1. If you are integrating over symmetrically over the origin, and your integrand is an odd function, your integral will be equal to 0. Okay? If you don't believe me, you can try doing a u sub, like 1 minus x squared du would be negative 2x dx, and then dx will be negative du all over 2x. If you change the limits on the integral, so say u of negative 1, that would equal 1 minus 1, which is 0. And then u of 1 would also equal 0. So you would have an integral from 0 to 0. Okay, your integral would turn into 0 to 0 of x times the square root of u times negative du over 2x. Whenever you have an integral going from a to a like that, of any function, that's just going to equal 0. Okay? So no matter how you slice it, you're going to end up with a 0. Okay? Even if you didn't bother with noting all this theoretical stuff and you went and integrated it brute force, that's what's going to happen. This thing ultimately will be a big fat 0. Okay? So this whole thing will just be 0, and you just get 4 pi squared. Where is it? So let's see if I'm right. Please be right, please be right. Yay. Okay. That'll do me for the video then. Okay. Thank you for watching as usual, and I'll see you next time.